Now let's consider another version of the comparison test, which looks at using a limit to draw the comparison instead of using an inequality. And what this has that's better, perhaps, is that now I don't need that condition that says that if I want to show divergence, then I need to show that the terms of the series are bigger than something that I know is divergent, or that if I want to show convergence, I need to show that the terms of the series are smaller than something that I know is convergent. Here, I don't have to worry about the inequality. Here, I just have to be able to evaluate the limit. So the way that we're going to do the limit comparison test is, again, we need to make sure that our series an and bn are series with positive terms. And when we take the limit as n goes to infinity of the terms of an over the terms of bn, we get some positive constant c. And that essentially says that either both the series converge or both the series diverge. So in other words, the way I like to think of it here is if we can conclude if the limit as n goes to infinity of an over bn is equal to some positive c, and it's a finite c, it's not equal to infinity, for instance, and essentially the two series behave the same. Meaning, if one of them converges, the other converges, or if one of them diverges, the other diverges. Let's try this out with an example. Notice that in this series here, we've got 1 over 2 to the n minus 1. I can't make the same inequality argument that we did before, because here 1 over 2 to the n minus 1 is actually bigger than 1 over 2 to the n. So now we're saying that the terms are bigger than a series that we know is convergent. But this inequality is going the wrong direction for showing convergence. Okay, so remember, if we want to show convergence, we want to show that the terms of the series are less than the terms of a series that we know is convergent. So the inequality is going the wrong direction for showing convergence. So if we want to show convergence, we'll need to use the limit comparison test instead. So here, using the first version of the comparison test would not work here. But we can use the limit comparison test. Here I'll let my an be 1 over 2 to the n minus 1, and my bn will be just 1 over 2 to the n. So we kind of know what we want to compare it with. If I just take away that constant term, then the dominant term, 1 over 2 to the n here, is all that remains. So now when I take the limit as n goes to infinity of an over bn, in this case an was 1 over 2 to the n minus 1 over bn, which is 1 over 2 to the n, and I simplify it, flip it over, 2 to the n over 2 to the n minus 1. I'll do a little bit of algebraic manipulation here. For instance, dividing the 2 to the n, I can get 1 over 1 minus 1 over 2 to the n. Since this goes to 0 as n goes to infinity, this will leave me with just 1 over 1 minus 0, or 1. And since here we get some positive constant, some finite positive constant, that implies here that both the a and the AN series and BN series behave the same. Okay, and since what the series we were comparing it with, the Bn was 1 over 2 to the n, we know that one is convergent. The AN series must also be convergent. Okay, so since series 1 over 2 to the n is convergent, right, we showed this earlier, it's a geometric series with common ratio r equal to 1/2. We know that the other series must also be convergent. In this case, by the limit comparison test. Suppose I want to determine whether this series is convergent. Now this one's a little bit complicated to try and make that inequality argument. It's not that it wouldn't work, but maybe it's too complicated to try and establish that inequality argument in the first place. So instead what I'll do is I'll just focus on the dominant terms of the series to figure out what we're going to compare it with. So here let's compare the AN, which is what we have here, 2n squared plus 3n over the square root of 5 plus n to the 5th. We're going to compare this with Bn that has just the higher degree terms. So on the numerator, 2n squared, take the higher degree term, you know that's going to be the dominant term as n gets very large. The 2n squared term is going to get much bigger than the 3n term, so that's going to be the one that dominates the behavior of the series. Downstairs we'll have the n to the 5th term, so we'll have the square root of n to the 5th. And what we notice is actually this simplifies. It's 2n squared over n to the 5/2. And then if I simplify these, we get 2n to the 1/2 downstairs. Or 2 over n to the 1/2. Okay, so in fact we're comparing it with this divergent p-series. So let's do the limit now. So taking the limit as n goes to infinity of an over bn. So here was our an, 2n squared plus 3n over the square root of 5 plus n to the 5th. And then I'm going to divide that by 2 over n to the 1/2. Here I can just flip that over. So that'll be multiplied by n to the 1/2 over 2. So how will we evaluate the limit now? Well, let me distribute the n to the 1/2 here. So we have 2n to the 5/2 plus 3n to the 1/2. And then 2 times the square root of 5 plus n to the 5th. Now to simplify it, I'm going to divide the top and the bottom by n to the 5/2, and that'll get it into a form that we can evaluate. So now the limit is 2, just the constant 2, plus 3, and then n to the 1/2 over n to the 5/2 would be n to the 4/2, so over n to the n squared. And then here, dividing n to the 5 halves, well, that's dividing n to the 5th inside the square root. So I have 5 over n to the 5th plus 1. And now we see that as n goes to infinity, this guy goes to 0. This guy goes to 0. So I'm just left with 2 over 2, which is 1. And again, here we get a positive finite constant. So that means the two series behave the same. And in this case, since the series we were comparing it to was a divergent series, 2 over n to the 1/2 is a divergent p-series. We know it's divergent here since p is 1/2, which is less than 1. Therefore, we know that the other series is also divergent. And in this case, the argument being made was using the limit comparison test. So I'll say by the limit comparison test. Okay. So we see that the limit comparison test was useful for this one because trying to make that inequality argument here is difficult just because the expression is much more complicated than the one we're comparing it with.